Welcome to this lecture on one of the most exciting frontiers in nanotechnology, energy harvesting using piezoelectric nanostructures. Today we're going to explore how we can capture energy from mechanical vibrations at the nanoscale and convert it into usable electrical power. We live in an age where energy demand is constantly growing, yet we're searching for sustainable, clean energy sources. What if I told you that the vibrations from your footsteps, the motion of your heartbeat, or even the wind rustling leaves could power electronic devices? Our global energy consumption is around 580 exajoules per year. That's 580 times 10 to the 18 joules. Meanwhile, enormous amounts of mechanical energy are wasted every day as vibrations, motion, and heat. Studies estimate that about 60% of total energy is wasted, much of it as low-grade mechanical vibrations. This is where piezoelectric nanostructures come in. So what exactly is the piezoelectric effect? Let me explain this fascinating phenomenon. Piezoelectricity is the ability of certain materials to generate an electric charge in response to applied mechanical stress. The word comes from the Greek word piezein, which means to press or squeeze. When you apply mechanical force to a piezoelectric crystal, the internal structure deforms. This deformation causes a displacement of positive and negative charge centers, creating a voltage across the material. This effect was discovered in 1880 by the Curie brothers, Jacques and Pierre Curie. They found that certain crystals like quartz, tourmaline, and Rochelle salt exhibited this property. Now let's dive into the physics. Why do certain materials exhibit this effect? For a material to be piezoelectric, it must have a non-centrosymmetric crystal structure. This means the crystal doesn't have a center of symmetry. When compressed, the positive and negative charges don't cancel out. The polarization P equals D times sigma, where D is the piezoelectric coefficient and sigma is the applied stress. The generated voltage V equals G times T times sigma, where G is the voltage coefficient, T is the thickness, and sigma is the stress. Let me tell you about the most important piezoelectric materials used today. Natural quartz has a piezoelectric coefficient D of 2.3 picocoulombs per Newton. It's stable, but has a relatively weak effect. Lead zirconate titanate, or PZT, is one of the most widely used piezoelectric ceramics. Its D coefficient ranges from 300 to 600 picocoulombs per Newton, which is over 100 times stronger than quartz. For nanostructures, zinc oxide nanowires are particularly promising. They have a D coefficient of 10 to 15 picocoulombs per Newton and can be grown in large arrays. You might be asking, why do we need nanostructures? Why can't we just use bulk piezoelectric materials? This is a crucial question. The answer lies in the unique properties that emerge at the nanoscale. Let me explain. First, nanostructures have an enormous surface-to-volume ratio. A nanowire with a diameter of 100 nanometers has a surface-to-volume ratio thousands of times higher than a bulk material. Second, nanomaterials are mechanically flexible. They can undergo much larger deformations without breaking, which means more strain and more voltage generation. Strain equals delta L over L0, the change in length divided by original length. Nanowires can sustain strains of 5 to 10%, compared to less than 1% for bulk materials. Third, nanostructures can be integrated into flexible, stretchable electronics. Imagine clothing that generates power from your body's motion, or sensors embedded in bridges that harvest energy from traffic vibrations. Let's focus on a specific example: zinc oxide nanowire arrays. These are among the most studied piezoelectric nanostructures. Zinc oxide nanowires can be grown vertically on a substrate. When mechanical vibrations cause them to bend, each nanowire generates a small voltage due to the piezoelectric effect. Typical zinc oxide nanowires have diameters of 50 to 200 nanometers and lengths of 1 to 5 micrometers. They grow perpendicular to the substrate in dense arrays. Now let's get quantitative. How much power can we actually generate from these nanostructures? This is the critical question. Let's work through the mathematics. The average power P equals 1/2 times C times V squared times F, where C is capacitance, V is voltage, and F is frequency. Let's calculate the power from a single zinc oxide nanowire. Assume it's 100 nanometers in diameter and 2 micrometers long. The capacitance C equals epsilon 0 times epsilon r times A over D, where epsilon 0 is the permittivity of free space, epsilon r is relative permittivity, A is area, and D is separation. For our nanowire, the capacitance is approximately 10 to the minus 18 farads, or 1 attofarad. Under typical mechanical strain, the voltage generated is about 0.1 volts, or 100 millivolts. If the vibration frequency is 100 Hz, which is typical for human motion or machinery vibrations, plugging in the numbers, P equals 1/2 times 10 to the minus 18 times 0.1 squared times 100. This gives us about 5 times 10 to the minus 19 watts. That's 0.5 attowatts. This seems impossibly small. But here's where the power of nanotechnology becomes clear. We don't use just one nanowire. We use billions of them in parallel. A typical zinc oxide nanowire array has a density of about 100 billion nanowires per square centimeter. That's 10 to the 10 per square centimeter. The total power from an array equals N times the power from a single nanowire. So the power from 1 square centimeter is 10 to the 10 times 5 times 10 to the minus 19. This gives us about 5 nanowatts per square centimeter. Now we're getting somewhere. If we have a 10 by 10 centimeter array, that's 100 square centimeters, generating 500 nanowatts. This is enough to power ultra-low power sensors and electronics. What about real-world performance? Let me share some impressive results from recent research. Professor Zhonglin Wang at Georgia Tech has been a pioneer in this field. His group has achieved remarkable results with zinc oxide nanowire generators. In 2006, they demonstrated the first nanogenerator, producing 1 to 4 millivolts from mechanical deformation. By 2012, they achieved a power density of 11 milliwatts per square centimeter using optimized arrays and resonant designs. That's millions of times better than our simple calculation. How did they bridge this gap? Through clever engineering, optimizing nanowire geometry, using resonant frequency matching, improving electrical contacts, and innovative device architectures. Let's get more rigorous and look at the fundamental equations governing piezoelectric materials. The electric displacement d sub I equals epsilon ij times E sub j plus dijk times sigma jk. This relates electric displacement to both electric field and mechanical stress. The strain Sij equals Sijkl times sigma kl plus dkij times ek. This relates mechanical strain to both stress and electric field. These are tensor equations showing the coupling between mechanical and electrical domains. The d coefficients are the piezoelectric coupling tensors. An important question is, how efficiently do we convert mechanical energy to electrical energy? The efficiency ETA equals E electrical divided by E mechanical, the ratio of electrical energy output to mechanical energy input. The electromechanical coupling coefficient squared, K squared, equals D squared over epsilon times S. This fundamental parameter determines the maximum possible conversion efficiency. For PZT ceramics, K squared is approximately 0.5 to 0.7, meaning up to 50 to 70% coupling efficiency. For zinc oxide, K squared is lower, around 0.05 to 0.1, or 5 to 10%. This is one limitation of zinc oxide, but it's offset by its other advantages, like biocompatibility and ease of fabrication. Now let's explore the exciting applications of piezoelectric nanogenerators. One major application is self-powered sensors for structural health monitoring. Imagine sensors embedded in bridges, buildings, or aircraft that harvest energy from ambient vibrations and wirelessly transmit data about structural integrity. Wearable and implantable medical devices are another frontier. A pacemaker powered by heartbeats or a glucose sensor powered by body motion would never need battery replacement. The Internet of Things requires billions of low-power sensors. Piezoelectric energy harvesting could make these devices truly autonomous, eliminating the need for batteries or wired power. Environmental sensors in remote forests, oceans, or mountains could harvest energy from wind, rain, or animal movement, operating indefinitely without human intervention. A self-powered sensor system consists of a piezoelectric harvester that converts ambient vibrations into electrical energy, which powers the sensor and wireless transmitter. Despite tremendous progress, there are still significant challenges to overcome. First, power density. While we've achieved milliwatts per square centimeter in the lab, many applications require watts or tens of watts. We need orders of magnitude improvement. Second, durability. Nanowires must withstand billions of mechanical cycles over years of operation. Fatigue and degradation are serious concerns that researchers are actively addressing. Third, impedance matching. The high impedance of piezoelectric generators doesn't match well with typical electronic loads. Sophisticated power management circuits are needed to efficiently extract and store the energy. Fourth, manufacturing. Growing billions of aligned nanowires reproducibly and at low cost remains a major engineering challenge for commercial deployment. Exciting new directions are emerging in materials and device architectures. Flexible piezoelectric polymers like polyvinylidene fluoride or PVDF offer mechanical flexibility and can be processed over large areas using printing techniques. Hybrid organic-inorganic Perovskites show remarkably high piezoelectric coefficients, in some cases exceeding traditional ceramics, and can be solution processed. Two-dimensional materials like molybdenum disulfide exhibit piezoelectricity in their monolayer form, opening up atomically thin energy harvesters. Three-dimensional, architected metamaterials with designed mechanical properties can amplify strain and optimize energy harvesting performance. Let's work through a concrete example. Can we power a wireless sensor node with a piezoelectric shoe insert? A typical wireless sensor node for environmental monitoring consumes about 100 microwatts on average, including sensing, processing, and periodic wireless transmission. A shoe insert might have an effective area of 50 square centimeters for energy harvesting. The required power is 100 microwatts, or 100 times 10 to the minus 6 watts. The power density needed equals 100 microwatts divided by 50 square centimeters, which is 2 microwatts per square centimeter. Walking generates heel strike forces of approximately 2 to 3 times body weight. For a 70-kilogram person, that's about 1,400 to 2,100 newtons. Over 50 square centimeters, this gives a pressure of approximately 28 to 42 kilopascals. Walking frequency is about 2 Hz, or 2 steps per second. State-of-the-art piezoelectric shoe inserts have achieved 1 to 10 milliwatts of power, which is 10 to 100 times more than our sensor needs. This is a realistic application today. Let me zoom out and discuss the broader implications for sustainability and our energy future. Distributed energy harvesting could dramatically reduce battery waste. Billions of batteries are discarded every year, containing toxic materials like lithium, cadmium, and lead. Self-powered sensors enable truly autonomous networks that can operate for decades in remote or inaccessible locations, revolutionizing environmental monitoring, infrastructure health, and precision agriculture. Every vibration, every footstep, every gust of wind represents wasted mechanical energy. Capturing even a tiny fraction could power millions of devices. You might ask, could this ever scale to grid-level power generation? The honest answer is probably not. The power densities are too low for large-scale electricity generation. But that's not the point. The real revolution is in distributed low-power applications where piezoelectric harvesting is uniquely suited. It's about powering the right devices in the right way. Let me share why I find piezoelectricity so intellectually beautiful. It represents a direct, reversible coupling between two fundamental domains of physics, mechanics and electromagnetism. This symmetry is expressed in the constitutive equations we saw earlier. The phenomenon emerges from the broken symmetry of crystal structures and the quantum mechanical behavior of electrons in ionic bonds. It's a bridge from the atomic scale to macroscopic devices. The reciprocal nature means the same materials can convert mechanical to electrical energy as sensors and energy harvesters, or electrical to mechanical energy as actuators and transducers. This versatility is remarkable. How do researchers actually measure and characterize piezoelectric nanostructures? Let me describe some key techniques. Piezo response force microscopy, or PFM, uses an atomic force microscope to apply a local electric field and measure the resulting mechanical deformation with nanometer resolution. Direct mechanical testing using nanoindentation can measure the piezoelectric response under controlled mechanical stress. Electrical measurements under dynamic loading, using shakers or ultrasonic actuators, characterize the frequency response and power output. Let me share some recent breakthroughs from the past few years that show where the field is heading. In 2022, researchers developed stretchable piezoelectric devices that maintain performance even under 100% strain, enabling truly wearable energy harvesters. Machine learning algorithms are now being used to optimize nanowire array designs, predicting geometries that maximize power output for specific vibration profiles. Biocompatible implantable harvesters powered by heartbeats have been tested in animal models, showing promise for next-generation medical devices. Integrated systems combining piezoelectric harvesters with thin-film supercapacitors and batteries solve the intermittent nature of energy harvesting. What are the theoretical limits? How much better can we make these devices? The maximum thermodynamic efficiency equals k squared over 1 plus k squared. This is the fundamental limit imposed by the electromechanical coupling. For the best materials with k squared around 0.7, the maximum efficiency is about 41%. We're still far from this limit in practical devices. As we approach truly nanoscale dimensions, quantum mechanical effects become important. Ultrathin structures may exhibit enhanced piezoelectric responses due to surface effects and quantum confinement. As we conclude, I want to emphasize that this field is still young and full of opportunities for innovation. This technology requires interdisciplinary expertise spanning physics, materials, science, electrical engineering, and nanotechnology. If you're interested in any of these fields, there's a place for you. There's exciting work at every level, from fundamental science exploring new materials and phenomena, to engineering optimized devices, to deploying systems in real-world applications. The next breakthrough in efficiency, durability, or manufacturing could come from a student watching this lecture right now. I genuinely believe that. Let me summarize the key points we've covered today. Piezoelectricity is the conversion of mechanical stress directly to electrical charge, arising from non-centrosymmetric crystal structures. Nanostructures like zinc oxide nanowires offer high surface area, mechanical flexibility, and integration with flexible electronics. Power densities have improved dramatically, from nanowatts to milliwatts per square centimeter, through optimized designs and materials. Applications in self-powered sensors, structural monitoring, and wearable devices are not just futuristic concepts, but realistic technologies today. Challenges remain in long-term durability, achieving higher power densities, and scaling up manufacturing for commercial deployment. The field is rapidly advancing with new materials like flexible polymers, 2D materials, and architected structures opening new possibilities. I want to leave you with a final thought about the poetry of what we're doing here. We're taking the whispers of motion, vibrations so small they're barely perceptible, and converting them into usable electrical energy. We're harvesting energy from the ambient chaos of the world around us. We're bridging the quantum mechanical world of atoms and electrons to macroscopic applications that improve human lives and protect our environment. This is technology that works with nature rather than against it, that seeks to capture waste rather than generate more, that distributes rather than centralizes. Thank you for joining me on this journey into the fascinating world of piezoelectric nanostructures. I hope I've inspired you to think about energy, materials, and sustainability in new ways. The future of energy harvesting is bright, and it's being built one nanowire at a time.